Okay. There we go. All right, so let's get started. First thing I want to do is make your connection from where we've been and what we've been doing to what we're about to do. Because this whole school year, this class is just like one continuous order of what we do in an experimental design of doing a scientific research problem. Okay, so first, we learned that statistics is not just numbers, that it's important how you get those numbers. So that's what we just tested on, experimental design. Getting the numbers, making sure your sample's representative, how you get those, and so then at the end of our experiment, you then compare the data or whatever. Well, now that we have collected the data, that's what we just talked about, that collection process. Now that we have collected that data, we are going to talk about how to graphically display it. A couple things. How we're going to graphically display it and what those numbers mean as far as, are they way spread out? Are there outliers? What's going on with those numbers? Is this something I should be worried about or not? Okay. So, here we go. Chapters 2 and 3 reference the categorical data. And it's important to say it's categorical data because remember how last unit when I said you need to pay attention to if it's a sample or the whole population. Remember how that's important. Are we talking about a sample or are we talking about the whole population? Here, it's important to say, are we talking about categorical data or are we talking about quantitative data? Because the math you do for a categorical variable is different math than you do for a quantitative variable. So they are two totally different tracks. So you'll identify from the beginning, is this categorical stuff? If so, then you follow this set of math rules. And if it's quantitative, then you identify that and you say, and if it's quantitative, then you follow a different set of math rules. Okay, so let's make sure that we know how to identify that. So here we go. Categorical is things that are made up of categories, which that kind of makes sense, categories. They are things that you typically tally. When we went on our bear hunt, and you did your little flyover and you tallied what you saw, the colors that you saw. Okay? So examples, colors of M&Ms. Okay? Types of something. Type of something, for example, type of shoes in this class. I could tally the types of our shoes in the class. It can be numbers, but they are numbers that are labels. They are numbers that are used as labels, numbers that don't average. For example, raise your hand if you're in the 76008 zip code. Okay, so next, raise your hand if you're in the 76108. Okay, how about, there's another one, 76126. There we go. Oh, 76087. Okay, well there you go. So we have four different zip codes in here. I could tally how many we have in each zip code. Would it make sense to get the average zip code for the class? And it's like 76087.3564. Okay, no. And so would it make sense to get an average for zip code? Alright. Quantitative. Quantitative variables are actually, obviously quantities that are amounts, and it does make sense to average them. For example, could we get an average height of our class? Could we get an average time to run a mile for the class? How about your average speed that you go? Geico, or Progressive, the little, what's that thing you put in your car? Okay, smart Okay. Snapshot. Yeah, snapshot something. Okay. So we can get an average speed. Well, those are quantitative values. Those are things that make sense to get an average on. Okay? So, this quantitative, this stuff right here, all this quantitative stuff I said is one type of math. That we are not going to get to until next week. So we are totally not talking about anything quantitative until another chapter. All we are talking about now is the categorical stuff. So here are ways to display categorical data. A frequency table, which we have down here. This is the frequency of colors in an M&M bag. Okay, there's 55 M&Ms, and so they tallied them, and so they got these distribution of counts of those colors. Okay. So, what do you think this relative frequency is? What do you think it's relative to? Relative to what? It is relative to a number. What number? Well, it's relative to the total, so that we can get a decimal. All these then come up to decimals that total up to 1. So, the blue relative frequency is 13 out of the total 55, which is 0.24. Because down here, it already has the percent, which is what it turns into, and that's 24%. Okay? So let's do the next one. So what's the relative frequency for red? 7 out of 55. 0.13. So 13%. I would imagine there's some rounding there somewhere. Okay. So fill the rest of those in. You can see that this is the relative frequency or the percent chart. Okay? So fill the rest of those in while I draw a picture, because I'm going to tell you the difference between a histogram and a bar chart. So fill those in while I'm drawing you a little picture here. Okay. All right, let's talk about, because I don't know how I missed this, but somewhere in my schooling or just my something, I was just brain dead that day. I did not know that there's a distinct difference between a bar chart and a histogram. Aha. Do you see that there are spaces on this bar chart? Because this is categorical data. So therefore, the order can switch around. Is it necessary that I have brown in front of the green or red behind the orange or whatever? No. The order can switch because it's categorical. But with histograms, it's quantitative, so it's in numerical order. So this is 0 up to 5. This is 5, and everything in this bar here is 5 up to 10, and this bar is 10s up to 15, but not including 15, and so on. So it's in numerical order. That's a histogram. Do you see how these bars touch? Because they go right up to the next value. Here they do not on bar charts. Okay, so be aware of that. We are not doing these this week, but I just want to plant that seed, because this is a common point of confusion that people may not realize, that there is a difference between a bar chart and a histogram. Okay, next. A segmented bar chart displays the same information as a pie chart. So you have all of those parts of a whole, okay, totaled together. So this is segmented, stacked on top of each other. And here is a double bar chart. It's very good for comparing items. For example, here is males and females. So this is your double bar chart that we are comparing items. Okay. So next, there's this thing that is frequently violated. It's called the area principle. This is what happens on media, on scientific things, where they misrepresent data. They're telling you something, and they draw you a picture of it that's a totally wrong picture, and then you think something different than what is reality. So let's talk about what's wrong with these. This is a picture of the number in each classification on the Titanic. Okay? And so, which classification had the most members in it on the Titanic? No, not third class. The crew did. Now, however, if you look at this very pretty three-dimensional picture, what does it look like has the most in it? Which one looks like the biggest? I think, does third class look like the biggest? Okay? It's misleading because it's not really the biggest, and it appears to be. How about first class amount versus second class amount? Is it off because second class is supposed to be smaller? Does this look smaller? I don't think so. So it's very misleading. So making a nice, pretty, three-dimensional graph is not a good idea because it could put all of the area out of proportion. So look at this one down here. There's several things. In fact, I know specifically two. What's wrong with this? Okay. First, 50% is not half of the graph. What else? Yeah, it totals over 100%. Okay, and that's a no-no on pie charts. A pie chart is a total of 100%. You cannot have more than 100% in a pie chart. If you have overlapping information, you have to draw a different type of picture. Okay? Not a pie chart. Okay. Well, with that being said, there's like two main things we're talking about today. Bad graphs is one, and then this concept of independence. I want to show you a few other bad graphs before we go on to independence. Here we go. Here's some big bad graphs that I found. So you don't have these, but there's some other ones. First, to have the only true pie chart that there really can be, right? So there's that one. Okay, next. This graph could have saved lives if the NASA analysts had put it together and used the information. Let me explain. Yeah. What this is, each one of these dots is, say, like, represents 100 trials of these things called O-rings. And an O-ring is kind of like this little seal on the fuel tank of the shuttle. Okay, you know the big shuttle where I can't even draw it. It's got the shuttle like this or something. And then when they launch it, it comes in and it's this thing right here. But when they launch it, it's straight up and down, like this or whatever. And then it has the big tank.
Oh my God.
It has the big gas. Has the big gas tank right there, okay? So big gas tank so it can go up in the air and go into space. And then it drops off that gas tank. All right. I should have a picture there so I don't have to draw it. But anyway, here's what happened. The seal on the gas tank is an O-ring. And what happened is they realized after a horrific accident, so I remember in 6th grade, this is probably before your parents were even, story time, before your parents were even together, or they were probably in 6th grade themselves. It was TV day, and we were so excited because we saw the big TV cart coming down the hallway, and we knew we were going to get to watch TV in the class, so they brought it in. And yeah, it's a TV cart with a big TV on top. Well, the Space Shuttle Challenger was launching that day, and it did explode. It was a really big deal because they had a teacher that they had trained, Chris McCullough, to go into space, and she was going to then do some lessons from space, and it's a real big deal back then, first kind of thing of its type. And so we all gathered around, and we watched the news program, and we watched it go up into the atmosphere or air, and then as it's going, it just totally exploded. And, you know, here we're sixth graders, so we were just kind of like,
Awesome.
was it supposed to do that? I mean, I know. You didn't know. Anyway, so it was crazy. It was just like a beat down. It was kind of, you know, a real poignant part in American space exploration and so on and so forth. Certainly not as horrific as 9/11, but I mean, it made a big impact at that time. So, this data was available to the scientists before that event, and they just had not put it all together in this fashion. Here's a chart. Each one of these little dots, just say, is like 100 tests of the O-ring. And then this is the probability of failure. So you can see at these warmer temperatures, these things had a 0% probability of failure. Okay? Now, here's an outlier here and here, okay? And the reason I say they're outliers is because they were mathematically computed, and we'll talk about mathematical computation of outliers later, but anything outside of this red is considered an outlier. Now, they expand this red region. It's pretty wide over in this area. The red region is pretty wide because it's extrapolation. They don't really have any real hard data over here. Since they don't have any real hard data, then they kind of have to make this really big prediction, you know, span. But this black line is kind of like the average of what they would expect to happen. Well, guess what? That morning of the launch, it was a nice, crisp morning in Florida. Cape Canaveral, boom. That's what temperature it was. So here we go. We have like, what? 70% chance of, actually, you know what? I'm so not, it's this right here. That's what this black line is right here. Boom. So, over an 80% chance that there would be an O-ring failure. Okay? So if they had analyzed that data and actually put that stuff in a chart to get predictions, then they could have done that. Now, you do have to be careful because this is what's called extrapolation. It's pretty far out from the data they have, but still, it'd be worth investigating to where you'd want to figure something out and not put people at risk. Okay, so that's one graph. Here's the next one. This one, I think, would have a more closer impact on you because it's about college. So here we go. This, no, it's actually at Cornell University in Ithaca, New York. Okay, so this is a magazine, Ithaca Times, and so this person, and I don't even have like the details of who did it because they should be fired, had the whole front of the magazine with this article that says, Rising Signs, why does college have to cost so much? So the idea behind the article is that on top of the Cornell University tower, they have this graph here, which is the cost of tuition at Cornell, and it's obviously rising. Okay, and then underneath it is this graph down here, which is rank. So the implication is that your education is getting worse as the cost is going up. Okay, so let's look closer. Right here. Sure, this is over 35 years, and this is over 12 years. Even with that discrepancy aside, look, this is the rank. You know, and it's from U.S. News and World Reports. We've been ranked, you know, on the silver report of the U.S. News and World Reports. We're in the top 100 schools in the nation, and so, yes. Don't you want to be closer to 1? And you want to be a lower number, and when you become a lower number, say a 6 instead of, say, you know, a 14, isn't what this is actually what? A good thing. So is the education getting worse? No, it's actually getting better. So there was a total misrepresentation with the graphs and total incorrect conclusion. So don't go be a journalist or even a news person who did this. Let's look at this. I don't even know what to say about it. Okay, so this is like a for real picture off of Fox News. It was 47 degrees that morning or whatever in 2012 presidential run. These are the people that backed. I mean, hello, help me, please. So first of all, additionally, tell the whole fact that how much percent is this altogether? Like, how much? 193. Okay, we got 193%. All right, good. So, and a pie chart has to be of the total of the 100%. So this person like is so clueless. And then the area principle is also messed up because look at the 70%, the red area, which is the biggest. In my eyes, looks smallest. So it's just like this person should not have a job anymore. Anyway, so there you go. There's a few big bad graphs. So let's go on to the next topic for today. Next topic. Oh, there's tons. Every day you can find. Okay, next. Second concept for today. How do you mathematically determine if two variables are related? Okay, second concept. How to tell if two variables are related. Okay, because let me tell you something. If they are independent of each other, then they do not affect each other. They are independent. They do not affect each other. Okay, so we're going to look mathematically at what that is. Here is some manipulated data. January 2012, a simple random sample of 3,000 Americans 18 and older were asked, what do you look forward to watching in the Super Bowl? And here are the results. There are two variables here. One of the variables is gender. Is you're male or female. Hopefully there's no crossover there. And then over here is the interest. What you are interested in watching or not watching on the Super Bowl day. So the interest. So the question is your gender affecting or related to the thing that you're interested in watching in the Super Bowl? Okay, so here we go. First thing is I boo-booed, and this should be males and females here. So what we first have to do is say, okay, when the sample of 3,000 was taken, what proportion, it's not a perfect 50-50 split, what proportion of your sample was males that answered your question, and what proportion was females? So how do I figure out the proportion of males and females? Okay, there's a total. This does say marginal distribution. That is a vocabulary word. And those come from the margins. They come from the totals. They are only referenced by one variable. So this is all about the interest. These are things about interest. And all of these down here, those two are the what? Gender totals. Those are the marginal numbers because they are in the margin. So what is the marginal distribution of males? 1,800 out of 30 or 3,000, so that's 60%. Females is the 1,200 out of 3,000, which we know is going to be the other part, which is 40% because there was no overlap, and we know there's not 193% in our information here. So, yes. Next, we want to see, conditional upon you being a male or a female, is that affecting your interest in the game or the commercials or not watching at all? And so that is called conditional distribution. Conditional distribution is happening where two things are covered. See this in the middle? These numbers are covered by two variables, both the gender and what they're watching or doing. So this number is the male ones that watch the football game. This is the male that watch the commercials and the males that don't watch and so on. So these are conditional upon two variables. All right. So let's figure this out. How many total watched the game that I got? 1,200. Okay. 1,200 responses chose watching the game as their preference. Of those, what proportion were males? 720 out of 1,200 is, guess what? 60%. And 480 out of 1,200 is, guess what? 40%. Well, here's what this means. 60% of the game watchers are male. Is that true? Is that a true statement? 60% of the game watchers are male. Yeah, that's a true statement. Oh, sorry. 60% of the ones that that watch it for the game. That watch the Super Bowl for the game as opposed to watching it for commercials. Okay? So 60% of the ones that prefer to watch their interest is watching the game are males. Well, guess what? That is the same rate of males in my sample. So, since the male percent that watches the game is the same rate as the male percent in the total sample, and that is happening at an expected, or that's as expected. That means the gender is not affecting their choice of watching the game, because there's 60% in my sample and 60% are choosing to watch for the game. Next, commercials. How many commercials total? So these are going to be out of 1,000. Well, guess what the males are? 600 out of 1,000, so that's 60%, and the females are 40. So now here's the thing that sometimes people say. They go like this. Well, hey, they say males are watching the game at a higher rate or watching commercials at a higher rate because this is 60%, and this is only 40%. It's the same as the ratio, the proportion in my sample. 60% watched for the commercials, and 60% are overall in the sample. If those coincide, then gender is not affecting the interest. And this last one, tell me what that was going to be. 480 out of 800, good, is 60%, and then the 320 out of 800 is 40%. So let's graph these. Let's look like, so we have a sentence here. 60% of the game watchers are male, just like 60% of the sample is male. Let's put a picture to it. Ready? You're going to make a segmented bar chart. This graph, this bar is 100% of the game watchers, the ones that watch for the game. The one that watch for the game. This bar here is the 100%, all of the percent of the ones that watch for the commercials. This last bar is the entire 100% of the ones that do not watch. So those all are in percentages, because if I put them in numbers, they'd be different heights. Getting different amounts, we have different things. 1,200, 1,000, and 800, so it's not how many, it's percent. Let's now segment this by gender. 60-40, males, females. 60-40, males, females. 60-40, males, females. Gender is not affecting interest, choice, or whatever, choice of Super Bowl activity. Gender is not affecting the interest. So if gender is not having an effect on what they are choosing, then gender and interest are independent of each other. Gender and interest are independent. Because they are not affecting each other. They are not affecting each other. So they are independent of each other. Okay. So let's see what this will look like on the different side when they do affect each other. Let's see what it mathematically looks like when they do affect each other. Same situation, but I changed the numbers slightly. The marginal numbers are still the same. The marginal numbers are still 60% males. Actually, the gender ones are still the same. The others are different. So we still have 60% males and 40% females. All right, so let's do our conditional by gender. Here we go. How many are watching the game for the game? So out of the 1,100 that are watching for the game, what is the male ratio for that? It's 900 out of 1,100, which is 82%. Since this number is different from this number, something is happening. 60% of my sample are males, and yet 82% of the game watchers are males. So I could say males are choosing what? To watch the game at a higher rate. Okay, because that 82% is different than the males overall. So likewise, I can say the females were 18% if I did the math. Commercials end up being half and half. 600 out of 1,200 and 600 out of 1,200. And here's a common misconception. Watch this. Here's a common thing people get confused about. See this? This does not mean males and females are watching at the same rate. Because you do not compare males to females. You compare males for the commercial to males overall. Do you hear me? You do not compare males to females. You compare males for commercials to males overall, and those are different, so therefore something is happening. Likewise, this one ends up being 43% and 57%. So let's make a picture and see what the picture looks like when something is happening. Okay, so here is your 100% for those that watch the game. Here is your 100% for those that watch the commercials. Here is your 100% for those that do not watch at all. So, put in the segment of the gender in there. 82-18, 50-50, 43-57. So, something's happening. Gender is related to, or affecting, affecting the interest. Something is happening. So are they independent of each other? They are not. And then here is like a big no-no. Okay, let me see if I can fit this on here. Never, ever. Yeah. So if I was your parent, I'd say, don't you ever, I'm your stat parent. Does that sound like what a parent would say? Don't you ever talk to me that way or whatever. Don't never say dependent. There is nothing in this world that is totally mathematically dependent unless it's a perfect one-to-one ratio, and we pretty much never have that. For example, if one person walks into the cafeteria and they spend $3, if two people walk into the cafeteria for complete dependence, they have to spend $6. Three people in the cafeteria spend $9. Do you see that same slope? 1 and 2, 2 to 6, 3 to 9. That's a slope of perfection, 1 to 1. That's perfect ratio. We never have that in real life. Never, ever. Real data is not perfect. So we never say dependent. Here's what we say instead. Gender and interest, they're related. You could say they are related because something's happening, or you could say not independent of each other. They are not independent of each other because something is happening. They are not independent of each other because something is happening. One last time. They are not independent because something is happening. They are related. So, that's all for today on the notes, but I want to look at the homework. So, pull out your homework so I can tell you what you're going to do on that. Sorry. Here we go. Okay, first picture. Somebody should lose their job if they put this picture out there. It's bad, so tell me what's all bad about it, okay? Okay, well, anyway, you'll write that on your homework. Okay, next. Here is this problem about magnet schools admission decision versus ethnicity. And what I want to talk about is what the questions are out of. Let's do a couple of denominator problems. Look here. Question A. What percent of all applicants were Asian? So what is the denominator in that question? 1755, okay? And then you'll put a number up here. B. What percent of the students accepted? So what's that total of that group? What percent of the students accepted? So that means we're talking out of 931 that are accepted, and you'd put the Asian portion of that. Next, what percent of Asians? So that means you're looking at this thing right here. So what percent of the Asians? And so that means 292 is your denominator, were accepted. Okay, that's all I'm doing on that. And you'll finish filling them out. I mean, I'm just not trying to give you all the answers. Next, this is car origin versus the type of driver, students and staff. So I wonder, I think this would be cool to go out there and collect data and see if there's a relationship between the type of car and if you're a student versus staff. So we should do that. Okay, field trip. So please look though. You are going to be finding marginal, conditional, and checking for independence. And then I want you to stop at that problem, and here's why. You're going to get confused with some of these numbers. You may get it, and that's great. But sometimes you wonder which way should the numbers go. I want you to do just this one problem, and we'll check it tomorrow to make sure you're thinking correctly before you do a whole bunch more. So you don't start thinking and drill your brain in the wrong way. Okay, so stop before number 31. What? Oh, I don't know. 2 decimals? 1 decimal? I don't know.